Okay, guys, so today we're going to do some more polar graphs. All right, we're going to do some more polar graphs. And we're going to focus on the polar graphs in the form of A times the sine of n theta, or A times the cosine of n theta. Okay, how is that different than the ones that we talked about last time? There's something inside the angle, right? There's something inside the angle. So let's see what that does to a graph. All right? If n equals 1 in this situation here, we would have what kind of a graph? A circle, right? We discovered that the last time we were together. Okay, so check this out. I want to see if you can kind of catch on to what's going on here. So this is a graph of 3 times the sine of 3 theta. Okay? What do you notice is going on? We have 3, these are called rose curves, by the way.
What?
All right? Rose. R-O-S-E. Like a flower, yeah. Rose curves. When they look like this, because it looks like a flower. It doesn't look like a rose at all, but it looks like a flower, right? So these are called rose curves, all right? So check out what happens when I increase A. So I'm going to make A, if it will let me. So I made A become 4. What happened? Could you see anything that happened? I made it 5, 6, 7, 8. Okay, so what do you think A determines? The length of the petals. Does that make sense? It's the length of the petals. Okay, so now let me go back down to 3, and let's see what N affects. You think it's the number of petals? Okay, let's see. So let me go back down to 3. All right, so I'm going to increase N. Whoa, N is 4. Look how many petals we have now. All right, let me go to 5. It's the prettiest thing we've done so far. This is 6. This is 7. This is if N is 8. All right, and it won't let me go any higher. So can y'all make any conclusions about, we obviously know what N controls, right? What does N control? The number of petals. But we want to be able to predict the number of petals by just looking at a graph. Oh, what do y'all think? It doubled. We have double the number of petals when this is an even number. But then when this is an odd number, it's that number, okay? So right now we're looking at 16 petals, right? It won't let me go any higher. It won't let me go. You can do it in your calculator if you want. But there's 7, right? Also notice the symmetry here. Is there symmetry in this graph? No symmetry? There is symmetry? What type of symmetry do we have? Y-axis. We could fold it along the y-axis and we would get the same thing on the other side. And I wonder why it's y-axis symmetry. It's the sine function, right? It's a sine function. But now check this out. What if I go to 6? How many petals do I have? 12. Talk to me about the symmetry this guy has. Y-axis and x-axis. And it even has a third type of symmetry. What's the third type of symmetry? The origin. It's reflected over the origin as well. Okay? So it has x and y axis symmetry, then it automatically has the origin symmetry as well. Okay? Does that make sense? Okay. Cool. All right, so now what we're going to do is we are going to do a little bit of discovery here. So I want you to work through this real quickly. I'm going to give you this. You guys work together. Use your calculator to graph these, and then I want you to sketch the best you can. When you're sketching the best you can, what's going on. There's the front and the back side. Okay, guys, so for this first one, I'm not going to attempt to draw this, even though you did, and I appreciate you participating very well in that. I'm going to wait and show you how to draw those in a minute, but this is the graph. Notice how many rings out do you need to go? 3. So when you draw it, make sure you're 3 rings out. Also, what else do you notice about this? There's 5 petals. Okay, and it's a cosine function, so what is it symmetric over? Just the x-axis, right? Just the x-axis. What if my petals had been, like, what if n had been 6? What kind of symmetry would I have had? You'd have all of them, right? All 3 of those types of symmetries. Okay, and then the next one is y equals 3. Instead of cosine, now it's sine. So how does that change? How does that change our picture? It changes the symmetry, right? It shifts it around. It changes the symmetry so that we have the y-axis symmetry, right? Okay. And then what if we have r equals 2 cosine of 4 theta? We should be 2 rings out when we draw it. And we should have a total of 8 petals. And what kind of symmetry do we have for this one? All of the symmetry, right? Meaning x-axis, y-axis, and origin. Okay? And then what happens though if we were to change this to sine? Would it change it? Does it change the graph? What do you think? Yeah, it does, right? How did that change it?
But it's still, the symmetry is still the same.
It still has the same type of symmetry as the other. What did you say, Tate? I interrupted what you were saying.
Like I said, it goes in the gaps of the other graph.
It goes in the gaps of the other graph. So wherever a rose petal was in that first one, right, now it's a gap, okay? And so, yeah, so when it was cosine, we had a petal on the x-axis. But when it's sine, we don't. All right? That's really neat. That's really neat. Okay? All right, so let's talk about conclusions that you guys made. So for this one, what's the basic shape of this? R equals A cosine n theta. This is not going to write because that's going to be... Okay. What we got? What kind of a graph do we form there? It's a rose curve. It's a rose curve, and what can you tell me about a rose? What about that rose curve? What all can you tell me about the rose curve? Okay, we're gonna have, we know for sure x-axis symmetry, right? And we also know that one of the petals will lie on the x-axis. Okay. What about the A? What can we say about the A? That's the length of the petal. Instead of saying length of the petal, is there a better word we could use for that? A math word that we've used about trig graphs before that kind of talks about length? Amplitude. So instead of length, we probably should call that amplitude. All right. And what about n? What if n is odd? Then that's the number of petals, right? Okay, if n is even, then it's what? Double. And I'm going to write this in the middle because that goes for both of these, right? That goes for both of these. So then what's the difference about the next one? It's still a rose curve, right? But what's different? We're gonna have y-axis symmetry, we know. And it may be that we have more symmetry, it just depends on what? What depends on the symmetry here? Sorry, what makes the symmetry? N, right? The number of petals that we have. If it's an odd number of petals, then you're only going to get the y-axis symmetry. But if it's an even, then you're going to get all three, right? Okay, what generalization can you make about the number of petals on a rose curve? I believe we've already made that generalization, right? I jumped ahead. Are we okay with that? And then 4, how does the graph of a sine curve differ from the graph of a cosine curve? Rose curve for both of us. Right, and also the symmetry, right? So if you have a cosine rose curve graph, then one of the petals will lie on the x-axis for sure. Okay? I don't think that's true for the sine rose curve. Is that true for the sine rose curve? I don't think it's true. It may be true. Okay, so let's flip over to the back side. What form is this equation in? What is this? That's one of those Lindner skates. Lindner skates. Okay. So to look at this in your calculator, you have to take the square root. So if we square root the function, and the function is 4 sine 2 theta. But when you square root, you know it's plus or minus. So I need to do a negative, same thing. Alright, let's graph this. Did anybody else's do that? Like, did it not close up? Okay, if it doesn't close, then it has to do with how your theta step is, so if you go to your window theta step, if this is not a very low number right here, like I had to change somebody's to 0.01, I think it was, what it does is it slows it down so that it can grab all the points, okay? If it's a really high theta step, then that means that it's going real fast around the angles and it's skipping over points and it won't give you a full graph. All right, that's what that means. So I have mine to 0.13. This is actually the default setting, I think, on my calculator. Okay, and then you might want to lower it to 0.01 if you want to. All that's going to happen is it's going to slow your graphing down. Okay, it'll get there, but it takes a while to get there. Or you can just believe me and know that, yes, it will close up. Okay? All right. So there's the graph of that. What do you notice about it? I wonder how far out this goes. Like, I wonder what that is. And I wonder how far out that goes. What do y'all think? I would say 2. Do y'all think it's about 2? I wonder what 2 has to do with. It's the square root of 4, right? It's the square root of 4, and A affects that. And then on B part, you had to do the cosine one. Is that right? So how did that change? What did that change? Do we still have a figure 8 looking thing? It just in a different position, so it like rotated it or something? So it changed the symmetry perhaps? And say mine didn't completely connect it either. But it is like a figure 8 with the x-axis symmetry. What kind of symmetry did you say that first one had? We forgot to answer that. What type of symmetry did that first graph have? It had origin only, right? It did not have x-axis and y-axis symmetry, right? It had only origin. But then what about the other one? What did it have? It had all three, right? This one had x-axis, y-axis, and origin. All right, are y'all good? Okay, so I got some more things I want to show you because I want to show you how you're really supposed to graph this. I think we've made some really cool generalizations, and we've got some clues about what these graphs should look like. And now I see if we can really properly graph these things. Okay, so the first one that I want us to look at is a rose curve. All right, so let me pass out. What we're going to do in class today is just two graphs. Okay, We're gonna do a rose curve and then we're gonna do another one. So let me pass these out to you. This unit, you get a lot of handouts because there's just a lot of things you have to look at. And then I feel like we'll probably be able to watch a couple of videos, okay? Because this won't take too long. All right. So if we were gonna graph this first one, oh, I'm so sorry. Guys, no. Okay, now we can start. Okay. All right, so let's check out. Now look, this looks a little bit different than what yours does because the file got changed. But this looks like what you have on your paper, right? So if I wanted us to graph this, what are we expecting this to look like when I graph it on this polar graph right here? What are we expecting it to look like? A rose curve. Can you tell me what else we're expecting to see? How long will the petals be? 3. So I know when I graph it, it'll be 3 rings out. What else? How many petals will I have? 4. And what kind of symmetry will I have? Y-axis for sure. X-axis, and all of them because I have 4 petals, right? But I know that those 4 petals will not be on the X-axis. Okay? So, yes?
Okay, if you have X symmetry and Y symmetry, you can assume that's the origin.
Yes, you may. Yep. However, if something has origin symmetry, you cannot assume it has X and Y. Just like the lemniscate that we did. Okay? Very good question. All right. So let me show you something that's really cool. Are y'all ready? So we're going to go back to graphing sine and cosine, just regular curves. All right? So check this out. This is the graph of 3 times the sine of 2 theta. Is that the same one we just did? Oh, that's the same exact one. Okay, okay. So check out what I'm going to do. What do you notice about the sine curve? What's the amplitude of the sine curve? 3. And if I go all the way to 2 pi, so that's what the x max is here, how many cycles did I go through? Went through 2 cycles, didn't I? Because of the 2 right there. It changes the amplitude. I mean, it changes the, what's the word I'm looking for? Period, right? So it will finish 1 cycle at pi, right? Then it'll finish the next cycle at 2 pi, okay? I believe the x-axis is scaled by 1s, which is why this doesn't look like, it's not like an x scale for the trig. Normally with trig windows we do a pi halves x scale, right? And this one's scaled by 1, so that's why it may look a little different. But I want you to check this out. I have this point as the origin, okay? Y'all are about to be impressed. This is really fun. I'm going to drag this point over this sine curve, okay? And as I do it, it's going to plot what those points look like on the rose curve, okay? So watch this. My mouse. Come on, mouse. Don't mess this up for me. Hang on, hang on. Ooh, I'm at the top of the curve. I wonder what that means about my rose petal. I'm at the tip of that. Now what's going to happen? Then we go back to the origin, right? Now my R values are negative. I'm at the tip of another one. All right. So how can we use what we already know about sine curves to produce a graph that looks like this? Where will the tip of the petals occur? At the maxes and mins of our sine curve, right? Okay, so let's do this. Are you ready? All right. So what we're going to do is let's look at Let's look at this sheet that I've just given you. Notice you have another coordinate. You have another graph right there. I want you to graph this in normal, like if this were y equals 3 times the sine of 2x. Okay? So if it said that, because we already know how to do this, and this is an awesome review for us for the final exam anyway, right? Y equals 3 times the sine of 2x. So I know my amplitude is what on this graph? 3. So we know that amplitude is 3. What else do we know about this graph? What is the period of this graph? How do we find period? We take 2 pi and we divide it by b, right? And b is 2. So what is now the period? Pi. But I want us to graph this all the way from 0 to 2 pi because in polar form I want us to be able to, so remember yesterday or last time we went around the unit circle, right, plugging in angles? I want us to go all the way around the unit circle, all the way to 2 pi, okay? So we're going to do it by looking at this graph to see if we can plot our points. All right, so if we're going to go all the way to 2 pi, the period ends at pi. So don't we have to have 5 famous points within one period? Isn't that right? So the first one's here, and then the next one will be up here, right? And then here, and then here, and then here. Isn't that how the sine curve works? So by the time I end this one cycle right here, what is this x value? So we know that this value right here, the y value is 3 and negative 3. I need to know what this x value is. Let me go ahead and draw what's going on here. What is the x value right there? Pi, because we said that's the period, right? It completed its cycle by the time we got to pi. So if this is pi, then what does that mean that halfway through that cycle is? Pi halves. And then the beginning point is 0. But I want us to go all the way to 2 pi. So let's keep going. All right, so if this is 2 pi, then what's this value right here? 3 pi. Okay, so this is what this looks like. Was this a good review? Did y'all remember all this stuff? You good? All right, we're going to use this to help us plot this sine curve, or this rose curve. Okay, so we're expecting how many petals? What do we know we're expecting? 4 petals. And we want the length to be 3. So the R value has to be 3. Can we figure out where the tips of those are going to be? They're going to be right here. At this coordinate, at this coordinate, at this coordinate, and at that coordinate, right? What is that first coordinate? So the R value would be 3, and the angle would be pi fourths, right? So these are going to be your tips. So where is 3 pi fourths? We know how to plot those points. All right. What's this value down here? 3 pi fourths. So let's plot that. How do we plot negative 3 pi fourths? So do the angle first. 3 pi fourths is over here. Then we have to shoot backwards. All right, and then the next one's going to be where? Okay, and what is that? What's the pi fourths that's between pi and 3 pi halves? The one that's in that third quadrant. 5 pi fourths, awesome. So let's plot that one. All right, and then the next one's going to be where? All right, so the value is negative 3. and 7 pi fourths. So 7 pi fourths would rotate and get you here, but then you shoot through the origin. All right, so now that I know where the tips of the petals need to go, what else do you think is important? Do you think that's enough?
No.
What do these x-intercepts represent?
Where they close.
Where the petals close, right? Where they go back to the origin. Okay? So can you draw it from this point?
Mm-hmm.
Okay. And you want to make the petals as symmetric as you can, as it's possible that you can. That's right. We'll teach you how to draw flowers. All right, everybody okay with this one? All right, let me show you how to do the last one. Okay? And then after I show you this, we'll watch probably a couple videos. All right? Sound like a plan? Okay, so let's check this out. Let's see. Okay, first of all, what is this? What am I expecting this graph to be? A loop. And how do you know that it's going to be a loop-de-loop? This is like what we did yesterday when we started out with a circle. And then we decided to add or subtract from that circle. Remember that? Okay. Well, I've got one more thing I want to show you because there's a discovery about, well, how long is the circle and how long is the loop inside of it, right? There's a connection between this number here and this number here, okay, as to how long the loop in the middle needs to be. All right. So let me show you this little Desmos thing that I have. Okay. So, can you see the green circle? Because this is what you're looking at, is the green circle. Can y'all see this? There's a bunch of other little things going on. That's the polar graph. Okay, so right now, we have this green circle, and we have the form R equals A plus 4 cosine theta, all right? And I have let A be 0 right now, all right? Which means we're not adding anything to it, so we're expecting the circle, right, that's been shifted over, that's over here. Okay, that's what we're expecting. So I wonder what happens if what if A were 1? So let me let A be 1. What happens when you add a number to it? So do you see this? Yes. Okay. Okay, good. So when A was 0, are y'all listening? When A was 0, the circle went all the way out to what value? 4, right? But now I'm adding a number to it. I'm adding 1 to it. So now the so-called circle that's supposed to be on the outside, it's not a circle anymore. But it now has a distance of 5 because I added 1 to it. Now, what about the length of that inner loop? What is that? And what does that come from? 4 minus 1. Okay? Are y'all with me? Okay, so what if I change A to 2? Tell me what I can expect.
2, 6. Yeah.
Okay, so you think it's going to go all the way to 6. So the big loop's going to be out to 6, and the inner loop's possibly going to be 2. Y'all think that?
One added, one subtracted.
Okay, let's see. So when A is 2, is it doing what you thought it was going to do? Okay. So it goes all the way to 6, and now this inner loop is 2. Because 2 plus 4 is 6, and then 4 minus 2 is 2. Okay? All right, let me change the A to 3. I think I can just type it in. Let me type in 3. All right? What if A is 4?
Eight.
Tell me what you predict.
It would be 1. That makes a little heart open.
Okay, so do we have an interlude if A is 4?
No, it's gonna be.
It's going to be dimpled, right? It's going to be like a little heart. It's going to be like a little butterbean graph. Okay? Right?
Okay, I have a question.
Yeah.
You have 8 plus 4. What happens if it's A minus 4?
Oh, okay. So what if... Hang on, let me keep going. Let me go to 5 and see what happens. Oh, check out what happens if it's 5. We start adding 1 out here.
4 minus 5 and then 1.
Yep. Okay, so Takaya, your question was, what if A is negative?
No, if like instead of having A plus 4, A minus 4.
Oh, okay. Let's see. What happens? It just goes to the other side, like the thing we did the other day, right? What if this was sine? Would anything change if this was sine? So it would be up and down instead of left and right? Do y'all agree? Okay, I'm trying to figure out how to get this to go. There we go. So if it were the sine graph, right? It does this and it does that. What if A is negative? So check this out. So what I have here is that we're calling this B now because it's a different graph. This is a negative 2. Okay? So then how far out did it go? It still went out 5, right? So it's like you take the absolute value of it if it's negative.
Okay.
And then when you subtract it,
So it's the same.
it's the same thing. It does the same thing if it's negative. Okay? Are y'all good? All right. So tell me what we're expecting with this guy.
Go out of 3.
Okay?
We're
We're going to go out to 3. Can you tell me the symmetry that we're expecting to see? Where is my, so it should be centered over here in the positive x, right? When would it be over here on the negative x side?
If it was minus.
If we had a minus. Very good, very good. Okay, so let's talk about what this looks like if this said y equals 1 plus 2 cosine x. Let's review that for just a minute because that's going to be helpful for me as well to plot this, okay? So what all can you tell me about that graph right there? What is the amplitude of that graph? 2. What is the period of that graph? 2 pi. We haven't changed the period at all, right? We didn't do any kind of horizontal shrinking or stretching. Well, what did we do? What does this do? We just added 1 to the y's, right? So we bumped it up 1. Right? This goes up 1. So let's talk about let's just do 5 famous points. Let's go to 2 pi, do the 5 famous points. So if I were to plug in 0, normally cosine starts at 1, doesn't it? But the amplitude is 2, and I've bumped it up 1. So where do you think the y value is going to be when x is 0? And if you're not sure, input the value. Plug in 0 for theta. What's the cosine of 0? 1. 1 times 2 is, plus 1 is 3. So now we're starting up at 3. All right. The next famous point should occur at pi halves, right? Pi halves, pi, 3 pi halves, and then we end at 2 pi, right? So then if I input pi halves into this, what is the cosine of pi halves?
Cosine of pi half 0.
Thank you, good. 2 times 0 is 0. 0 plus 1 is, so at pi halves, we're at 1. What about at pi? What's the cosine of pi? Negative 1. Negative 1 times 2 is negative 2, plus 1 is? Where is it going to be at 3 pi halves if this is a cosine curve? It's got to be back up here. And then where do we end? Right back there. So if we were to draw like a little midline, this would be the part where it would normally be on the x-axis, right? And notice the distance between the midline and the max and the midline and the min. What do you notice? What's that total distance? 2, because that's the amplitude, right? Okay, so that's what that guy looks like on the graph. Let's see if we can use that to help us come up with what we think is going to happen. So what do you think? Let's use this. That's a point. What is that point? That's 3, 0, right? So 3, 0 is here. And what did y'all tell me? You told me that the big loop is going to go to 3. Isn't that what you told me? All right. Let's plot this point. What is this point?
Negative.
So the R values are still positive because the Y values are positive. They don't become negative until they cross the x-axis, right? So that would be 1 and what? Pi halves? Okay, so yes, because the Y represents the R and the X represents the angle. And when we write it in polar form, we do it in the R. It really doesn't matter which one we do it in when it's in polar form. Okay, so we've got to connect these 2 dots together. Y'all ready? We've got to connect these 2 dots together. When you connect it, don't go way up here and then go back down to this point. You got to make sure that the R's stay within 3 and 1. Because these Y values are between 3 and 1. You know with me? So when you draw it, you got to make sure you go like to that right there. You can't just shoot out beyond the 3rd ring because the Y values are not past 3 on the graph. Okay? And then what's the next point that we have? So we have, what is the negative 1 is the R value and pi is the angle. Where is that? We go to pi. Okay. All right, so pi rotates over here, and then you got to shoot through the origin.
Okay.
Now, question, did we go to the pole from this point to this point? Meaning the origin, did we go to it? We did, because it happened right there, didn't it? So at some point, whenever we try to draw this to this, we got to go through the origin. Okay? So let's go to the origin. And get that point. And then what's another point we have here? 1, 3 pi halves. So let's plot that one. Where's that? So now what are we going to do? What do you think? Make your loop and come back and get this one. And try to make these as symmetric as possible. I don't think I did. And then we have to go back and get this point.
Let's go back to 3.
Good. Go back to 3. So that would be 3 and 2 pi, right? Which is this. And you want to try to make it so that the top matches the bottom. I tried, guys. I'm not an artist. I tried. Okay. So some of your homework that you have, you will have to actually draw some graphs. So I need to give you some graphing paper so that you'll have this all ready for you. Okay? Let me stop this video.
They